Start recording here. We're right here at 11. Hello, people at home. Of course, the chat room's open, so don't forget there. We're getting a lot more people in here. COVID rates were under 4% positivity rate for the last week straight. So the little bump come up from 3 went to 4, almost 5. So it's, and hopefully that trend will continue. So anyway, so it's nice to see more of you in person. You might want to take the third exam live in person because you have to take the final in person. So just anyway, so it'll give you some experience on taking it in the Scantron form. So I think that might be an option for you. Okay, so last week we did chapter 8, all in one seminar, one lecture. Okay, so what I want to do is I want to do this chapter 8 activity. And I've talked to a lot of people, somebody, how do I remember all these things? And I said, well, first thing, do the reaction table that I suggest you to do. It's really important to do the reaction table because you can take that reaction table, refine it, get it better, and take it on next semester when you'll need it for more of our retrosynthetic strategies and multi-step strategies. Okay, so that's why I really want you to do that. This activity is designed to teach you also the 3 ways you need to look at every reaction. Okay, there's a forward, a backwards, and a middle. And so I'm going to demonstrate all of those, and we're going to test our knowledge because you all studied over the weekend about all these reactions we had, right? And put them in your reaction table. So we're going to use this activity to kind of test that knowledge and to show you how, the 3 ways that I want you to learn how to do these reactions. So, and I will post the answers to this, but I also have a blank one, I think, already on Canvas under activities. Okay, it's under activities. So most of the time, you're going to go to a reaction that looks like this. It's a substrate and some kind of reaction conditions. So in this case, we have chlorine and CCl4. What's CCl4? Carbon tetrachloride. It is a non-halogenable solvent, and so we use it as a solvent. It's also a non-polar and a polar aprotic. A non-polar aprotic solvent. Okay, we use this because we want to have it do one thing and one thing only. We want to do the addition reaction of chlorine across the double bond. So that means, also when you attack these things, you want to look for what's going to change, right? Nothing over here is going to change. And let me do red. Red. No. All right, nothing over here is going to change in our system. The only thing that's going to change is that double bond. So that's the only thing you have to play with, right? So when we draw our structure, we're going to go dun, 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 draw that, draw that, draw that. And we know the double bond is going to go away. And we know we're going to put 1 chlorine on one side and 1 chlorine on the other side. Okay. Now they are adding anti, but because that bond has free rotation, you can write them any way you want. Okay. They're not, this one right here is chiral. So we're going to have a mixture of syn and anti. I'm sorry. R and S on this one because this one is chiral, but this one can be drawn in any position it wants because it can free rotate. Okay, so that's one way to learn that reaction, right? And so we could do that same thing with this mercurization demercurization reaction. We have the mercury is going to add onto this part right here. Oh, and then the OH is going to attack that one right there. So we're going to get that secondary alcohol. And so we're going to go dot, 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 and put our OH here. And then, of course, the mercury gets reduced off in the second step. Now, see, that means that we did the mercurization first in water with the acetate. It's going to hook the mercury on here, and then we're going to knock the mercury off and add a hydrogen here. Okay, so that's what the reduction with the sodium borohydride does. Okay, so now that's another way to do it. So that's halogenation. This is oxymercurization, demercurization. What's the last one? We've changed the solvent. It turns it into the halohydrin reaction, okay? Because you have bromine and then you'll make the little intermediate here, but you have a lot more water around than the bromide ion. So what's gonna happen is that water is going to act as our nucleophile. And which carbon will the oxygen attack? The more substituted carbon. The more substituted carbon have more of a partially positive charge on it. So it's going to attack this one here. We had that thing like that. So that means the bromine is going to be on here. and the OH is going to be there. Okay, so I'm going to erase that just for clarity here. Okay, so we need to see, so now we had to think about our regioselectivity of that reaction. We know what the intermediate is with the bromonium cation on top of there. And then we know that one carbon is a primary carbon and one carbon is a secondary carbon. So that means the secondary carbon is going to have more of a partially positive charge, which means our nucleophile is going to attack that one. We see that happen a lot, right? The nucleophile tries to attack the more substituted carbon most of the time. Okay, so let's do that again. Now let's do it with HBr. And again, the only thing changing is our double bond. And so we're going to add something here and something here. Where does the hydrogen go? On the primary carbon or the secondary carbon? Primary. Goes on the primary carbon because it adds first, giving us a carbocation, right? And then what happens now? Do we actually get our bromine here? It shifts, right? It's going to shift because we had a carbocation as an intermediate here, and we have a possibility of a tertiary. So we're actually going to put our bromine here, and we're going to leave. We're going to have a new hydrogen here. And I'm going to draw the hydrogen to show you it was a 1,2 hydride shift. Okay, so you have to be careful about your mechanism. Whenever you form a carbocation, you have to worry about it rearranging. And in this case, it did. Okay, so let's do the next one here. Oh, that's one that kind of adds a little funny, right? That adds all at the same time, syn addition. And it adds where the boron is going to be here. The boron is going to be attached here with those two other H's. So that means that that's where, when we oxidize it, the boron is going to oxidize up. That's where we're going to put our alcohol. Oops, OH. And our group here. And I'm going to put the hydrogen here. So that hydrogen there was the one that came from the boron. Okay, so that added right across syn. And so if we had stereochemistry, where we had like a methyl group here, we have to worry about where that hydrogen is. It'd be a 50-50 mixture because it's selective in how it goes. It's syn addition. It can attack this side of the double bond or this side of the double bond, giving you a 50-50 mixture if we were stereochemistry. Okay, so let's worry about that. No, let's not worry about that. Let's remember that. Okay, so what happens when we do water with trace acid? That has a name. The name is hydrolysis. It's the opposite of dehydration. So when we have trace acid, we're going to form a carbocation. Our carbocation is going to form here, which means it's going to move to give us that tertiary. We're going to end up with our OH here, and our methyl group didn't move our hydride group. So I'm going to add a hydrogen here just to show you it was a 1,2 hydride shift. Okay, so this is the most common way you're going to see this, but this is not the only way you're going to see these reactions written. Another way to see these reactions written is to see them this way. I'll go back and do those later. Okay, so in here we have the product and we have the reaction conditions. We just need to know what our starting material was, okay? So when we're looking at these reactions, you can think of, well, if I used a strong base and removed HBr, it could give me the bond here. So, and because we're doing this with hydrogen, the hydrogen has to go on the most hydrogenated carbon. This carbon would only have one hydrogen on it. This carbon would have two hydrogens on it. So that means we probably have to have it in a position where we have 1, 2, 3, 4, 5, 6, and an ethyl group up there, where our double bond was right here. Okay, if our double bond is right here, our hydrogen would add here, our bromine would add here. Okay, now in theory, you could have another starting material where the double bond was here. Okay, and that would give possibly the same product. But the one here with the double bond on the end of the chain, this is the only product that will form, is having that double bond right here. 1, 2. Do you see how we're working it backwards now? Okay, this is learning the reaction backwards, looking at it from a product and a starting material. Okay, so if we look at this one right here, mercurization, demercurization, gosh, so that means we'll probably, again, have our double bond on our end here because the mercury is going to be attached to one carbon and the OH is going to come to the more substituted carbon. Oh, by the way, did anybody see the video for all mechanisms this weekend? Okay, so in that video, there's also that intermediate, thinking about the intermediate, the transition states, which helps you decide syn, anti, and R and S, and cis and trans. So in this case here, that means we'll have to have our double bond there. So it looks like we can draw that same starting material right here. When it gets reduced off, we're going to add the mercury to this side, the OH to this side here. OH in the form of water to this side, and then of course, reduce off the mercury. So I'm going to go ahead and remove these so that it's clearer. Okay. Okay, so what about the last one? Okay, what does permanganate hot do? It breaks our double bond. So we need to put a double bond where that carbonyl is, okay? Now it tells us that we have CO2 also produced, which means there's only one carbon on the other side of that double bond. So guess what? It's the same starting material. But we used different reagents and backed it up to achieve different things. Yes?
Does it matter where you place the double bond, like on that like carbon, like should be on top or on the bottom? Is that better?
You mean put it up here?
No, like on the other side, just like.
Oh. Well, no, it's where it had to be here. Oh, actually, no, okay, I'm sorry. That's not the right product at all, is it? Because the double bond had to be where the carbonyl was. The double bond has to be there. We had one too many carbons. Okay, because think about it, we're going to be cutting this right through here. This will give this half, and this will give that half. So make sure you count your carbons when you do this. Okay, double check. We had 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. We have the right number of carbons on both sides. That's really important when you do cleavage reactions, that you want to count your carbons to make sure you have the right things. Okay, so let's do another backwards set here. Ooh, Lindlar's catalyst, gosh, and it made a cis alkene. So what do we start with? An alkyne. So let's count our carbons. 1, 2, 3, 4, 5, 6. So we're going to do 1, 2, 3, 4, 5, 6. See how we're doing this backwards? We're taking, oh, this is a cis alkene, Lindlar's catalyst. That means it did a syn addition of hydrogen across a triple bond to get to that. And so that's why we're going to go to Lindlar. Ooh, we have an HBr added here. And so it's adding, it also is adding across a double bond, a triple bond, right? So we have 1, 2, 3, 4, 5, 6. So 1, 2, and 3 is where the triple bond is. 5, 6, 1, 2, 3, 4, 5, 6. Yeah. So see how that backwards reaction is there? And I could have written it bromine here, hydrogen here, but it was just, that is the product. And so that's the only starting material we can get this product from. Although the starting material will give us 2 products. You'll have the bromine on the 2 and the bromine on the 3 because they're equivalent carbons. As far as they're both quaternary when they start. Okay, so let's see. Chlorine, and we're going to put 2 equivalents of it here in carbon tetrachloride. So that means we're tetrachlorinating it. So I guess that means we're going to have to draw that same structure again. So see what I mean by going backwards in the system? Okay. All right. So let's do the last way, the middle. We have to figure out what the reagent was. So we have to look at what changed. So we have an alkene. We have an alkene. right here, and it's going to a cis diol. Okay. Now we actually have two different reaction conditions that can do this, but what's the most common one? Osmium tetroxide. So OS4 right here. And then the second step is sodium, hydrogen sulfate, and water. Okay. So first step and then second step. And we know this because it gives us a cis diol. The other thing that'll do it is potassium permanganate cold. We'll also do that syn addition. Okay, let's see what changed here. We have an alkene and we're going to, a bromine and a alcohol. Gosh, that's kind of weird. Wait, we have a reaction for that, right? We have the Halohydrin reaction. So that just means bromine and water. Holy cow, in the last one, we just blew the ring apart. So what happened? So in this case, we're breaking the ring right here. We have 6 carbons, 1, 2, 3, 4, 5, 6. So we didn't lose any carbons, but we broke it in half. And if it broke in half the first time, it'd give us an aldehyde, but we got 2 carboxylic acids. So I think this is potassium, I think this is potassium permanganate with base hot. Okay, see how you can now, by looking at the change, you can see what the reagents are for the system. All right, let's do that. One more test on that. On these, okay? So there's a very, very sketchy double bond there. And it's giving us a bromine on the second carbon. So what's our reagent here? That's a simple one. We must be adding a hydrogen. So HBr. HBr.
Are these pretty like common? Like, do you really see that many variations in them?
Yeah.
Like, I mean, like, does that like there's like a pattern? You know what I'm saying?
Well, all I'm doing is I was just using it as an example of ways to look at your stuff. These are just the reactions and how to look at them. You need to know what the reagent does. So what's the starting material and what's the product? And by looking at it forward, backwards, and in the middle, you'll be able to really recognize them on exams, because all 3 of these ways are going to be written into the quiz. So, all right, so we have a tertiary alcohol. Okay, so that means we add it across here, right here, and the simplest reagent for that would be water with trace acid, or acid catalyst, or HCl, H2SO4 drop, something like that. Okay. Ooh, last one. Okay, we can't use water for that one because it'd end up over here. So we must be using something else, but it's a primary alcohol. Oh no, it isn't. It is cut here. Okay, there should be another bond here. Sorry, I left out a carbon.
Mercury.
Close. What's the other way to make a mercury? Would give us a secondary only. It would give us a secondary only on here because the mercury would attach to the most substituted carbon and the OH would come in on the least substituted carbon. So it'd be hydroboration. So that's BH3, THF is usually used. And then the second step is peroxide, H2O2 in base. Okay. All right. Do you see the 3 ways I want you to learn all of these reactions? And starting with the reaction table is the good way to do it. All right, let's just fill out the rest of these so that we can post it. So let's do some more things. All right, permanganate cold. What's that going to give us? It's going to give us a cis diol, just like the osmium. But the fact that it's cold is going to OH, OH. And because we have free rotation, we don't have to show stereochemistry. Ooh, palladium with hydrogen at 2 atmospheres at 50 degrees C. I think it's going to do catalytic hydrogenation. And I'm going to put the hydrogens there to show you that it happened. All right, last one. What do? Bromine in water. No, in methanol. What's the product going to be? Well, the first thing that's going to happen is we're going to put that bromonium cation on there. And then the second thing is our nucleophile is going to attack the most positive of those 2 carbons. The most positive of those 2 carbons is going to be the more substituted one, which means we're going to get something attacking here. So the lone pair from the methanol is going to attack that partially positive side in an anti-configuration. But again, we have free rotation, so we don't have to worry about stereochemistry, which is going to give us, a hydroxide. Actually, it's going to give us an ether, a methyl ether. So that's the derivative of the halohydrin reaction, okay, where you use, instead of water, you can use an alcohol as that nucleophile. All right, and let's do the last 3 pretty. What else? What does osmium tetroxide do? Cis-diol, right? So 1, 2, 3, 4, 5. OH, OH. No, we took the double bond away. Okay. And if that helps you, draw the product with the double bond and then draw what happened to your double bond and then erase the other part. That can work for some people. Okay, let's see for this one. We're going to have a bromine here and a bromine here because it's in carbon tetrachloride. Permanganate hot. Permanganate 50 degrees, 80 degrees, so even hotter. What are we going to make? Diol, aldehyde, ketone. Nope, carboxylic acid. Plus CO2. We're going to cut that right there. Okay. Everybody understand how I want you to study these reactions, okay? Because as we go forward, in fact, our next chapter is Nmr, so you can study these as we go through. And these, some of these will be on the quiz on Wednesday. So this should be posted already, this empty one. The full one will be posted when I get back to class, because I'll just post this one.
No worries.
It's under activities. And it's called Chapter 8, Activity. Okay, well, I think
Resources?
It's under resources, activities. Hydride. That's chapter 8. Pretty sure it's there. Okay. If not, it'll be there as soon as I get back to my office. Okay. Okay. So let's close that and done and get out our chapter 9, nuclear magnetic spectroscopy. It's nuclear, not nuclear. The president said it wrong. Okay. It's nuclear. Magnetic resonance spectroscopy, and we're going to do some mass spec too. We're going to learn a technique that is going to help us, well, not us in particular, but as chemists make new molecules, they use this to identify the carbon-hydrogen attachments and frameworks, as well as the carbon-carbon frameworks of these molecules we're creating. So the 2 most common types of Nmr spectroscopy we have is what we call proton spectroscopy, where it's hydrogen, the isotope 1, so it's hydrogen itself. And when we talk about acids and base, we call it a proton, and so they say it's proton Nmr, okay? Now, we also have another really powerful tool called carbon-13. See that little 13? It's an isotope of carbon. Carbon's usually 12, but it has a heavier isotope, 13 and 14. 14 is radioactive, and that's how we radiocarbon date things. But 13 actually has an odd number in it, which makes it NMR active, and so that we can use it for NMR spectroscopy. Okay, so in the NMR spectroscopy, nuclear magnetic resonance spectroscopy, what we're going to do is we're going to use radio waves and a high magnetic field. And so what we're going to have is our little nuclei and all our molecules are going to be either spinning all randomly until you put it in an electric field, and then all of a sudden they're going to go poof. They're going to be aligned with electric field, either in up or down in that electric field, okay, that magnetic field. And then what you're going to do is you're going to hit it with radio waves, and that's going to knock some of them into a higher energy state, okay? And then we're going to wait for it to go back down to its low energy state. And that time it takes to go to our low energy state, we're going to convert that into a spectra that we can understand, okay? So we're going to use those low energy weights. Now, but the fact that we have these things, we have to have an uneven number of spins in our nucleus. So in the case of our hydrogen, we only have one proton in there. So that's an odd number, so that we can make sure that we can see it go up and down, change its spin when it's activated. Carbon-13, it has one extra neutron. So that extra neutron makes it be able to have spin active right here. Now, we can also see this if your atomic number is odd, but your mass number is even. So there are some things like Deuterium Nmr, which is this right here, and nitrogen-14. They're not as useful, but the most common ones are hydrogen, carbon, fluorine-19 is a really good one because there's only one isotope of fluorine, and P31. It's not the most common isomer, but it's a pretty good isomer. Okay, so how are we going to use this? Well, oh, sorry, let's take a roll. Okay. Okay, so the most important thing for you in proton NMR is these four things. We need to look for these four things. If you ask yourself these four questions, how many spins do I have? I mean, how many signals do I have? What's the intensity of the signals? What are the position of the signals? And what is the spin-spin coupling? You should be able to identify compounds just by those, and you'll be able to say, yes, yes, no, no, yes, because it has to do with some of them. You don't even have to use all of them. Sometimes you can just use number of spins. Sometimes you can just use intensity, but most of the time it's going to be spin-spin coupling that helps you the most. So that's what you're going to look for. So in every spectrous NMR you get, it's going to look something like this, okay? So what we have here is we have all but one of those things represented on here. We have the number of peaks. So we have a peak here and a peak here. So that tells us there's two signals, okay? Two signals is important to us because we're going to learn about that. That means that there are two types of hydrogens, okay? Now, if we look at our shift, this is our position. And as we move further away from zero, it took longer for those things to relax, meaning it was close to a electronegative atom or an electronegative activity. And what that means is that there's more electron density around that hydrogen, so it shields it from relaxing, and so it takes a time, okay? And it will see de-shielding, which moves it to zero, and shielding moves it up field, okay? The other thing we have is spin-spin coupling here. In this case, we have 4 peaks or a quartet. In this one, we have 3 peaks, okay? And then we have intensity. Now, intensity is not the height of the peaks themselves. It's actually the area under the curve. There's an area under the curve function. So we call that an interval, okay? So it's actually measuring all the area under that curve because, you know, if your peak is split 3 times and this peak is split 4 times, even if they had the same area, they would have a lower, the 4 one would have a look smaller because it's split into 4 peaks, but it could even have more hydrogens. So we always look at the interval, not just the height of the peak. That's what we mean by intensity. So intensity, think about it as an interval right here, and position is shifting up and down the numbers here. Okay. Now, the area under, see underneath each of these lines, there's a little bit of area there. So it's actually measuring the area under those, under each of those lines and adding them all together because that's 1 peak. Okay. So what we want to do with proton NMR is it actually helps us because they generally have very sharp peaks and very smooth baselines. See how there's only this little teeny blip here? Right here. This is our internal standard, and I'll talk about that. But these tend to be fairly clean. There's a little blip here, a little blip here, but for the most part, it's very, very clean. Okay. Our chemical shift increases from right to left. So zeros on our right side, and we go outwards. Okay. So it's kind of backwards from your normal Cartesian coordinates, but it's what we do. And usually we have it between 0 and 10 ppm. And it goes up to 15. There's a couple things like carboxylic acids that go up to 15. Okay. Now the term upfield and downfield is used to describe the relative position of those peaks. If it's closer to 0, it's upfield, smaller numbers. If it's a bigger number further away from 0, we call that downfield. And if you want to remember that, up is a smaller word than down, so it's going to be a smaller number. Okay. So that helps keep that in line. Now, I said before there was a 0 there. Because we're dealing with frequencies, big, huge, megahertz frequencies, it's hard to actually get the exact frequency we want. And so what we do is we put an internal standard in there that's going to show up at the same place every single time, and we'll call that 0. The thing we use for that is called tetramethylsilane, okay? So what that looks like is SIME, not 2, and then ME, ME, and ME. What's really cool is that all of the hydrogens on the methyls are going to be our 0 point, okay? And it's because the silicon is trying to take away their shielding by pulling electron density there. That's why we call it 0. It's de-shielded, it's upfield. I think I said that. Anyway, it's there. The other cool thing is that we also use this as the 0 for carbon as well. The silicon carbon and the silicon bond here is what gives us our 0 point. Okay. All right. So now let's talk about number of signals. So we're on the first one, number of signals. Okay. So how do we get the different number of signals? Well, that means that the hydrogens have to be in different electronic environments. Okay. So let me describe that here using this one right here. Okay. So we have 3 hydrogens bonded to a carbon, bonded to an oxygen. Okay. So those 3 hydrogens all have the same electronic configuration, right? They're all bonded to the same carbon. That carbon is bonded to an oxygen. So that's one signal. Okay. Now let's look over here. We have 3 hydrogens bonded to a carbon, bonded to an oxygen. So all 3 of those hydrogens have the same electronic configuration, but it happens to have the exact same configuration as that. Okay, so we're just looking at the bonds that we see, right? So in this case here, we have 1 NMR signal, even though we have 2 different carbons. We have 2 carbons, but all those hydrogens are in the same electronic configuration. Okay, so how can we change the electronic configuration? Okay, let's do this one. CH3, CH2, 2, and Cl. Okay, so let's look at these hydrogens here. It's kind of like the ones we just looked at. We have a carbon with 3 hydrogens that is bonded to a carbon. Okay, so that's one signal, right? So this is one signal. And then we have 2 hydrogens that are bonded to a carbon that has a chlorine and a carbon ion. So those aren't the same as the methyl group because it's just 2 hydrogens and it has the chlorine there. So this is a second signal. So this is going to have 2 NMR signals. Okay, so, okay, well, that's easy enough. CH3, O, CH2, CH3. Okay, so this and this are going to have the same signal, right? They're both CH3s. Oh, wait, this one's bonded to an oxygen, and this one's bonded to a carbon. So that means those are each going to give independent signals, 1 signal, 2 signals, and then this CH2 is different than either one of those, so that's going to give us our 3rd signal, okay? Now, all of the hydrogens on this thing are equivalent hydrogens. So it's going to give us 1 peak, and that it's going to give us 1 peak, but we don't know if it's going to be split or not yet. We'll talk about that next, okay? So that's pretty cool, but what about if we do something like cyclopentane or chlorocyclopentane? That looks like maybe just 1 signal, maybe 2, right? These 2 are the same, these 4 are the same as these, this one right here, so we're going to only have 2 signals. But we have a problem. When we have things like this, we have to draw it with all the hydrogens on it so we can look at its true configuration here. Cl, H, 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 H. Okay. So now these 2 hydrogens are not the same as these 2 hydrogens. So this is not just 1 peak. Why? So these 2 hydrogens see a hydrogen through space. The upper 2 see the chlorine through space. So that means we get 1 signal for these, 1 signal for these, and 1 signal for that. Okay. So be careful like that. Also, look at when you have double bonds. You'd say, oh, look, these 2 hydrogens are exactly the same because these 2 hydrogens on this side are the same, right? Because they're bonded to the same carbon. But through space interaction gives us 1, through space interactions gives us 2, and being in a different carbon gives us 3. That has 3 NMR signals because each hydrogen is in a separate electronic configuration. So this one is different than this one because of the chlorine. And this one is different than this one because this is bonded to one with the chlorine. And these 2 are different because this one has the chlorine and this one doesn't have the chlorine. So we have 3 different signals. So looking for those equivalent carbons is very important. And there's in the homework, there's a whole list of like 10 of them there to help you get that down. All right, so okay. So let's look at this one, okay? Let's see. Do those give 1 signal? Let's see. They're bonded on the same carbon and they both have an interaction with chlorine through space. So yes, they give 1 NMR signal. Okay. But what if we changed it to they can both see halogens through space, right? So they're going to give 1 signal or 2 signals? 2, because this is a different interaction than this here. So that's going to give us 2 signals.
Could you have 1 signal with different halogens?
If you drew it like this, but that's the same halogen. Those would be equivalent. That would give one signal. Cl, that would give two signals. Okay. So then if we go back to our other one with just one on it, how many signals do we get here? 3. Right, because this is different than that, which is different than that, which is different than that. So, okay. So let's see, what else? Okay. So that's looking at the number of unique types of hydrogens in there. That's called number of signals, the first thing you look at. Okay. So now you know that there are X number of carbon or X number of types of hydrogens you have to fit into your product. The next thing we have to worry about is position. Okay. Position is where it shows up on the map. So if it's upfield, it's shielded. It's got electrons protecting it from the spinning or changing that spin. And if it's downfield, it's de-shielded, downfield de-shielded. And that means that it's going to be a higher number, okay? So lower number, it's more like it has silicon there, which is shielding the system. Higher number, it's more like there's electron donating materials that are de-shielding the system. So protons near electronegative atoms are de-shielded. Okay, you're going to see that trend. You can actually walk down the thing looking at the different electron configurations and see how far they go. And I'm going to demonstrate that as we get through some of these things. Okay, so when we look at this, just comparing these two signals here, which one's bonded to the electronegative atom? The one at 1.7 or the one at 3.4? The one at 3.4 is bonded to the electronegative atom because it is de-shielded, it is shifted to a higher number. Oh, higher number for you guys. It's shifted to the higher number. So it's the de-shielded, it's the one that's hooked to the electronegative atom. So if we look at what the compound is here, the electronegative atom in question is bromine. So these are going to be further away from 0 than these. Okay, so this is going to be close to 0, and this is going to be further away from 0. The more electronegative you have, the more it's pulling electron density away from your hydrogens. And remember, we're looking at the nucleus of the hydrogen. So if you have less electrons around that hydrogen nucleus, it is de-shielded. It's going to react differently than if you had all its electron density and it's protecting it from that magnetic field. So if you think of it as having this, you know, not a cloaking device, a force field around it, and as it gets less and less energy in it, you get further and further away from 0. Okay. Okay, so we're looking for positions on there. And so the positions have relative ranges here, but I want to show you something really cool here. As we move away from a hydrocarbon, things are typically going to go up. So if you have just hexane or just methane, it's going to give you something way down here close to 0. That's about as shielded as you can get. And then as you add electronegative atoms to it, remember the carbon-hydrogen bond is not very polar. As you add electronegative atoms, it's going to start pulling electron density from that carbon and those hydrogens. So the cool thing is that our primary, secondary, and tertiary are all down here, hydrogens, okay? What's interesting is the primaries are here, the secondaries are here, and the tertiaries are here. So just by adding carbons, that's enough to de-shield your hydrogens. Okay, then the next thing is a hydrogen next to a double bond, because that double bond has a sp2 hybridized carbon, and that sp2 hybridized carbon pulls a little bit of electron density. An H next to a benzene ring, an H next to a carbonyl, or an H next to an alkyne. So changing the hybridization on the carbon it's bound to or the carbon it is next to will change it. Notice alkynes are up here because they're sp hybridized, but alkenes are up 4 to 7 because they're sp2 hybridized. Okay, so that's going to And then things that are bonded to oxygen, nitrogen, or have halogens on them are in this 3 to 4 range. So that means the bromine was at 3.4. So that was about right in the middle of that range. But that could be a nitrogen, an amine, an oxygen. So ethers and alcohols are going to show up here. The H on an alcohol or the H on an amine is in a really wide range. Why? The same reason they were broad in IR. Hydrogen bonding. There's different kinds of hydrogen bonding, how many times it's hydrogen bonded, whether it's a dimer, trimer, or whatever kind of complex it is, that's going to spread it out. If you have a very dilute alcohol in a non-hydrogen bonding solvent, you can actually get it down to a single little peak, but it's going to give us a wide range because of hydrogen bonding. Bonding, there you go. Now the H on an OH, way to hold it. That's more acidic than the H on an aliphatic, right? Because the alcohols have pK of 16, phenol had a pK of around 10, and the carboxylic acid had a pKa of around 5, right? So look where the carboxylic acid show up, way up here, above 10 most of the time. And so this is 9. So just looking at pKa, pKa is telling us this is less acidic, therefore it has less deshielding. This has more acidic, so it has more deshielding, and this is the most acidic and it has the most deshielding. So you can watch those OH groups walk across the screen by looking at that. Benzene rings, because of resonance, are shifted a little bit higher than the alkenes. They're using them in the 6 to 8.5 range. And then the last one is the hydrogen on an aldehyde. Okay, because it's bonded to this carbonyl, it has a lot of electron pull from it. Remember, it's partially positive. Right here, this is partially negative, and it's double bonded to the oxygen. It shifts it up the highest of any hydrogen bonded to a carbon. So we see that close to an electronegative atom moves us down the field. So you don't have to memorize the chart if you can get the positions, the relative positions correct. Okay, so we actually have a note here. You don't have to memorize these. You can get a relative position, and then by splitting or intensity, you should be able to figure it out. Okay, so again, don't try to memorize these entirely, but they are in the book. And one thing I do want to show, though, is this right here. Going from a primary alkyl group, it's lower than the secondary, which is lower than the tertiary. So you can actually see it walk down the way. The more hydrogens, the less of the electron withdrawing you have, and therefore the closer to 0. All right. Questions on that? Okay. I think this right here is a more valuable tool to help kind of get them spaced out in your mind. But if you're a numbers person, the table is in the book. So now I want to talk about intensity. Okay, intensity isn't the height of the peak itself, like I said, it's the integration of all the area under that curve. And the reason we do that is because if you're not split at all, you're going to look a lot higher than something that's split 7 times, even though that thing split 7 times might have more hydrogens in it. Okay, so we need to look at it from that grid. So we look for what we call a stepped curve, which is going to look something like that. And then what it does is it gives us a relative intensity to all the others. Okay, so it's not an absolute number. Okay, so what you're going to see is that, oh, this peak is 50, and this peak is 100, and this peak is 150. But proportionally, this would be 1 proton, 2 protons, and 3 protons, because if you divided them all by 50, you would get a whole number. Okay, and a good number for how many hydrogens you have. You know, you don't have 50 hydrogens on that carbon. You can only have 4. Most of the time, you only have 3. So you're looking for, you know, those kind of things. But remember, we also have equivalent hydrogens. So if you have 2 methyl groups that are equivalent, you can have 6 carbons under that curve. So that's why the intensity is so important. Okay. Most of the time, this kind of just prints it out for you. as a random number, and then, or you can assign one as, oh, I know that peak should have 2 protons on it, and then it'll give you a relative ratio for all of those. Again, this is a ratio and not an absolute number. So sometimes you might have to divide them all by 4 to get the right number. As long as you're, yeah. So, but what you might have to do is multiply or divide by a number. It'll give you a relative ratio. Like in this case here, we're going to say this is 1 and this is 1.5. We can't have a half a proton. So we know that's not a whole number. Okay. So in this case here, if we had this, let's multiply it by 2. If we multiply that by 2, that would take it up to 3. Oh. And multiply that by 2, that would take it up to 2. Okay, well, we still don't have the ratio we think we have in our product. So let's multiply it by 4, and that's going to get us 4 proton. Multiply by 4, that's going to get us 6 protons. Ah, that's closer because we have 2 different methyl groups here that are equivalent hydrogens. Notice that they have the same bonding and same spatial interaction on both sides. So that means that they're all the same. And that means all of these hydrogens are also equivalent. So we get 1 peak, intensity of 4, and intensity of 6. Okay, so you multiplying and dividing by whole numbers, as long as you're doing the same number to all of the peaks, you're doing it correctly. Okay. So if you know one of your carbons has a 1 hydrogen on it, you want to divide by whatever makes the smallest peak 1. Okay. All right, questions on that? So now knowing the intensity on these things, you can say, oh, well, I know I have either in this case, a symmetrical molecule, or I know, oh, there are 6 things that are kind of like a hydrocarbon, and there are 7 things that have double bonds nearby. Okay, so what are my choices? So you can look for choices saying, oh, look, there's only one thing that has, that many hydrogens in that zone. Okay. So now that brings us to the hardest but most telling part of NMR spectroscopy. The most telling part of NMR spectroscopy is the spin-spin coupling. Okay, so what this means is that non-equivalent protons up to 3 bonds away will split the signal that you're looking at. Okay, so let's say we have this compound here. Okay, so we have 2 hydrogens here, and we have 1 hydrogen that in this case is, I'm going to draw one of the hydrogens down here, and I have 1, 2, 3 bonds away. Okay, up to 3 bonds away. Okay, so in this case here, we have 2 hydrogens that are going to be split by, these 2 are identical hydrogens, right? They're on the same carbon, they have the same environment. Okay, so they're not going to split each other. They're going to give 1 peak because they're equivalent hydrogens. But we have 1 proton that is within 3 bonds. So this 1 proton is going to split this peak once. Okay, so it's going to go from 1 peak to 2 peaks, and they're going to be of equal height. Okay, so we're going to split that. So now we know there's only 1 hydrogen within 3 bonds of that peak because it's split that way. Okay, so now let's take a look at the other way. Let's look at this other one. So we have 1 hydrogen. So if we did an integration, we'd have 1. And we have 1, 2, 3 bonds to this hydrogen and 3 bonds to this hydrogen. How many times is that hydrogen going to split? We had 1 peak. 1 hydrogen is going to make it 1, and then the other hydrogen is going to make it a 3rd peak. We're going to have a total of 3 peaks now. Okay, these are equivalent to each other, but they still split the one that's not equivalent. Okay, you get 1 peak for the equivalent hydrogens on its carbon, and then split by however many hydrogens are nearby. We call it the N+1 rule. Okay, N is the number of hydrogens within 3 bonds. It can be 2, like in an alkene. There can be just 2 bonds away, like the end of an alkene. And those will split each other. So all of these are going to split differently, okay? Because this has 2 hydrogens within 3 bonds. This has 2 hydrogens within 3 bonds. This has 2 hydrogens within 3 bonds. We're going to get 3 different peaks, and they're all going to be split twice. So it's going to give us triplets. So n plus 1. N is the number of hydrogens within 3 peaks. 1 is for the peak itself. So in this case, we're going to have 2 peaks. For this one, we're going to have 3 peaks for this one. And if we blow it up here, a nice. Also, you will see that all of these are going to be symmetrical. Things that are even are going to be 2 at one peak, 2 in another, 2 in another. Things that are odd are going to have the triplet like this, where the center peak is going to be high and then evenly spaced coming out from it, however many you have. Okay. All right. So let's look at that n plus 1 rule again. We need to make sure we have our equivalent peaks to give us our peak. But then all hydrogens that are adjacent to it, 1, 2, 3 bonds, or 1, 2 bonds, or if we had something where we had a ring, like when we had that cyclopropane, if this hydrogen is different than this hydrogen because we had a cyclopropane and there's a bromine here, they'll split each other too. So it's 2 or 3 peaks, but no more than 3 bonds. Okay, so 2 or 3 bonds. Okay, so like in the case of that cyclopropane right here. All right, these 2 hydrogens were identical. And so they're going to be split by 1, 2, and then 3 hydrogens. So this is going to give a triplet because of that. In fact, each of these is going to give a triplet because of that. So that's another reason to draw out your rings. All right, questions on that? Now, there's some really common splitting patterns. So if you kind of recognize the splitting patterns by their structure, you'll see. Okay, so in the case of this one right here, you have, if it's not listed as a hydrogen, it's a carbon or something else. So this is something other than a hydrogen. Oh, I should do Z's. Anything but hydrogen here. So in this case here, we have a unique hydrogen that is 1, 2, 3 bonds away. So it's going to be split once. So n plus 1 is 2. And then we'll go the other way. We're going to look at this hydrogen, and n plus 1 is 2. No. How many hydrogens are within 3 bonds away?
Oh, there's 2 of them.
How many no, because we have 1 for this one for that signal. We're looking at that one. That gets 1 signal. And then we added 1 hydrogen to it. So that's an n plus 1. So that's 2. So you get 2 peaks. 1 for the hydrogen itself, and then 1 for the split. 1 for the splitting. Okay. Let's look at the next one, and we'll see if the pattern falls. We have 2 hydrogens here. Right here, and they are adjacent to 1 hydrogen. Okay, so that's 1 signal for the equivalent hydrogens plus 1 hydrogen gives us 2. Okay, and now if we look at this one here, we have 1, 2, this hydrogen and this hydrogen. So we have 2 hydrogens, so that's our n plus 1 is equal to 3. So we have 3 peaks. Does that make sense? All right. So these hydrogens are split by these 2. So we have n plus 1 is equal to 3. Because we have 2 here, and these are equivalent hydrogens. Okay. Now let's look at this one right here. We have equivalent hydrogens, 1 peak, plus 2 hydrogens here, so that's 2 plus 1 is equal to 3. So we have 3 for both of these. Okay, so can it get even more complicated than that? Yes. When you put a methyl group on the end of something, you get 3 right here. So you have 1 peak for this. So 3 plus 1 is equal to 4. So we're going to get a 4 peak because there's 3 hydrogens within 3 bonds. Now let's look at the other way. And look at these hydrogens. I'm sorry, those are the hydrogens you already looked at. Let's look at these hydrogens. We only have 2, so that's 2 plus 1 is equal to 3. 3. Okay, now let's look at this one. This is kind of cool. Let's do this one first. Right here, we have 3 equivalent hydrogens giving us 1 peak. We have 1 hydrogen nearby, so 1 plus 1 is equal to 2. So that makes this peak. We can even figure out which peak it is by looking at which is. Okay. Now let's look at the other way. We have this hydrogen here, and it's going to go to here. So 1 plus 3 is equal to 4. So we get 4 peaks. Okay, do we see how spin coupling works? Okay, so those are the most common ones, but let's do this. All right, so how many signals do we have first? We have 1 signal, we have 2 signals, and we have these 2 are equivalent methyl groups, 3 signals. Okay, so our integration would be 6 to 1 to 1, because we have 2 of these with 3 on there. Okay, and let's talk about these groups right here first. How many times are those split? How many hydrogens are within 3 bonds? No, that's a 4th. That's another bond out to the hydrogen here. So we have 1 hydrogen within 3 bonds. That hydrogen on the OH is a 4th bond, so we don't count it. So that means, what are these 6 hydrogens going to be split into? You have 6 hydrogens and you have 1 hydrogen within 3 bonds. So 1 plus 1 is equal to 2. So this should be a doublet. Interesting. Okay. Let's talk about this hydrogen here. How many hydrogens are within 3 bonds? There's 3 here, and oh, guess what? We don't count a hydrogen that's bonded to an oxygen. You do not split through oxygens or nitrogens. Okay? You do not split through oxygens or nitrogens. So that means these right here are the ones that count for it. So this hydrogen is going to be split by 3 plus 3. So that's 6 plus 1 is equal to 7. So this one's going to be split 7 times. And let's look at this last OH here. Well, we don't split through an oxygen or a nitrogen, so we're going to get 1 peak here. So we're going to see a doublet, a heptet, and a single peak. Oh, it's more than in the first example. I mean, in looking at the 6 hydrogens. Okay, if we put a hydrogen here, we have 1, 2, 3 bonds to oxygen. That would be 4 bonds to that hydrogen on the OH. So we couldn't count it just from the rule, the 3 bond rule. We can count this one because it's 1, 2, 3. So we do count that one. The new rule, I mean, the additional rule you need to know is that you don't split through oxygen or nitrogen. You do not split through oxygen or nitrogen. Okay. Okay, so that means we can look for things that have patterns. Okay. Okay, this is the same as this. So I'm going to have a peak that's 6 protons, 6 hydrogens. Okay. And there's only 1 hydrogen nearby So that means it's going to be 6 hydrogens in a doublet. And if we look at this now, this peak here is going to give us 1 hydrogen, but it's next to 6 hydrogens. So 6 plus 1 is equal to 7. So that's going to look like 1, 2, 3, 4, 5, 6, 7.
Wait, so you said 6 because there's 3 hydrogens on each side
Correct. And they're electronically equivalent.
within 3 bonds of the next side.
Correct. Okay, so that's 2 peaks. Oops. 2 peaks, and that one's there. So let's see what those peaks look like. So let's look at this. Hey, if we integrated this, you would say, oh, there's like 100 protons here because this peak's so high, and there's like 0 protons there because it's so low. But there's 7 peaks there. So when you do integrate under all these peaks, you'll get 1 proton. And if you integrate under all these peaks, you'll get 6 protons. Oops. Questions about spin-spin coupling? Okay, so now let's add a couple things together and talk about this. All right, so we have a nitro group here. It's an electronic drawing group, but it has electronegative atoms in it. So that means this one right here, is it going to be far away from 0 or close to 0? Far. So this is going to be the most downfield atom. So that's probably going to be this peak here. Now let's look at this one. This one here, it's got a carbon that's downfield, but then it has a carbon that's upfield, because this is almost like methane. So it's going to be the one upfield. So that's this one right here. Okay, so this is A. This is C, which means the last one has to be B. Great, we've already assigned it without even knowing the table. We've assigned our shifts, okay? Now let's assign our integrations, okay? Now that we know those peaks are there, our integration, oops. Uh-oh. No. Why can't I get to? Now we're going to look at our integrations. There we go. And let's try that back to C. Okay. And now we're going to do our integrations in blue here. There should be 2 on this peak because we have 2 hydrogens. There should be 2 on this peak, and there should be 3 on this. So our integration should be 2, 2, and 3. Ooh. If I actually gave you integrals, you might be able to figure out where everything is already. But now let's do peak-peak splitting, okay? In peak-peak splitting, we're going to do in green. Let's look at A first. And we have 3 hydrogens on that, so that's 1 signal, because those are 3 equivalent hydrogens, okay? And we have 2 hydrogens within 3 bonds to it, so that's 2, 1 plus 2, so that should be a triplet. Okay, so our C here should be a triplet. Okay, now let's look at B. B here, those two hydrogens are equivalent because we don't have a ring, so we don't have to worry about that, or a double bond. Okay, and we have 1, 2, 3, 4, 5, 6. 6 plus 1 is 7. We should have 7 peaks on this one. And going to the last one, we don't have any hydrogens on this side. We only have 2 hydrogens on that side. So that's 2 plus 1 equals 3. So that should be a 3. And when we blow that up, we see that peak A is a nice classical triplet. We have 1, 2, 3, 4, 5, 6. 6 peaks. Did we count them?
With on A, there's 3 hydrogens.
Okay, so there's 3 hydrogens here and 2 hydrogens here. So that's 5 plus 1 is equal to 6.
Why are you trying to?
Okay, we're doing the middle one. Okay, so this one right here is B, right? So if we look at the splitting on B, we see we have 6 peaks. Didn't we say 7 peaks? Okay, let's look at here. This is the peak we have. That's 1 peak. We have 3 on this side. Oh, and we have 2 on that side. So 5 plus 1 is equal to 6. So that should actually be 6 peaks. We miscounted our hydrogens. So we have 6 peaks, and notice it's nice and symmetrical right here. And our last one we picked was 3 peaks because it's this one, and there's only 2 hydrogens next to it, and 3. So we were able to identify shift just by its location. We were able to identify integration by their position, and we were able to look at the shift by, the splitting pattern for there, okay? So you can use any of those to solve the problem. You can look for shift, that solves the problem if you have the difference between a ketone and an ester, and stuff like that. Okay, so under most conditions, you do not shift through oxygen, even if it's within 3 peaks, okay? So if we look at this right here, we're gonna see this split by these 2 hydrogens for a total of 3. We're going to see this split by these 3 hydrogens, by these 3 hydrogens for a total of 4. And we're going to see these not split at all because it's going through oxygen. It's the same for that. So we should have a quartet, a triplet, and a singlet. So that means this must be the OH peak. This must be the CH2 attached to the OH peak. And this must be the CH3 peak. By splitting, by shift, and by...
You're getting lost when you're like crossing them, because like when you're talking about A,
Mhm.
like include the hydrogen B. So I don't understand.
Okay, in spin-spin coupling, you get 1 signal for all the equivalent hydrogens on the carbon you're looking at. And then it's split by however many hydrogens are within 3 bonds. Okay, so there's only 2 hydrogens within 3 bonds here. So that means we get our 2 bonds, or 2 is our N, plus the 1 peak is a total of 3.
For the A.
For A. For A. Now let's look at B. Right here. On B, we have 2 hydrogens, that's 1 peak, and we have 3 hydrogens on its adjacent. So that's 3 plus 1 is equal to 4.
Okay, that makes sense.
Okay, and we have 4 peaks. So that means just by knowing they're splitting, we can say, oh, this must be our OH because it's not split. This must be the thing next to the OH because number 1, it's shifted high, or because of its split. So this is the CH2 next to the OH. And this is the CH3 because it's closest to 0. So we assigned it by shift, plus it's next to the carbon with 2 hydrogens on it. So you can use any of those pieces of data, and as long as they all agree, you can solve the problem knowing only 2 pieces of information: shift and splitting, intensity and splitting, position and intensity. 2 pieces of information is usually enough to solve the problem. The other cool thing is if you used a small amount of deuterium oxide, deuterium is invisible at this frequency. And so what happens is that hydrogen will go away. All acidic hydrogens exchange with deuterium oxide and they will go away in the NMR. All right, I think I should stop there, and we're going to pick up with benzene rings on Wednesday after the quiz. And the quiz is only over chapter 8. Only over chapter. I want to work through some NMR problems first before I give you some NMR, okay? Only chapter 8. All right, write that down. All right, thank you very much. See you on Wednesday. I want to stop sharing and stop recording.